Security Capabilities of Information Systems. Welcome to this module on the Security Capabilities of Information Systems, IS. Modern computing environments rely on security features embedded within hardware and software to protect data and systems from threats. Understanding these capabilities allows organizations to implement stronger security measures. In this lesson, we will explore key security functions such as memory protection, encryption, Trusted Platform Module TPM, and access control mechanisms. Let's get started. Information system security capabilities refer to the built-in security mechanisms that protect data, applications, and infrastructure from unauthorized access and cyber threats. Organizations leverage security capabilities in information systems for these major reasons. Prevents unauthorized access, ensures only authorized users and processes can access sensitive data. Protects system integrity, guards against unauthorized modifications and corruption. Secures data at rest and in transit, uses encryption and access controls to safeguard data. Enhances system resilience, ensures business continuity by protecting against cyber threats. Now, let's look at an example. A company uses Trusted Platform Module, TPM chips in its laptops to ensure that only authorized operating systems can boot up. This prevents malware from modifying the boot process, maintaining the integrity of the system. Here's how to maximize the security capabilities of information systems. Enable built-in security features like encryption, TPM, and access controls. Regularly update and patch software to fix vulnerabilities. Implement multi-factor authentication MFA and role-based access control RBAC. Memory protection prevents unauthorized processes from accessing or modifying critical data in system memory. Operating systems use these techniques to protect memory. Address space layout randomization, ASLR, randomizes memory locations to prevent buffer overflow attacks. Data execution prevention, blocks execution of unauthorized code in memory. Virtual memory and process isolation ensures each application runs in its own protected memory space. Here's an example. A hacker attempts a buffer overflow attack, but because this is CSLR, the attack fails since the memory addresses are randomized and unpredictable. Here's how to enhance memory protection. Enable ASLR on all systems. Use secure coding practices to prevent memory vulnerabilities. Keep operating systems updated to fix memory protection flaws. TPM is a hardware security feature that provides secure cryptographic functions and protects system integrity. TPM enhances security through these core functions. Secure boot ensures only trusted operating systems can boot up. Hardware-based encryption stores cryptographic keys securely. Platform integrity checks detects unauthorized system modifications. Here's an example. A company's security policy requires all employee laptops to have TPM chips enabled. This ensures that only trusted software loads at startup, preventing rootkit infections. Here's how to effectively use TPM for security. Enable TPM-based secure boot on all devices. Store disk encryption keys within TPM for additional security. Use remote attestation to verify system integrity before granting access. Encryption protects data by converting it into an unreadable format, while decryption restores it to its original state when accessed by authorized users. Organizations use encryption to secure data in different ways. Symmetric encryption uses a single key for both encryption and decryption, e.g. AES. Asymmetric encryption uses a public key for encryption and a private key for decryption, e.g. RSA-ECC. Here's an example. A bank encrypts all customer transactions using AES, Advanced Encryption Standard, before storing them. When a user accesses their account, the system stores the data securely. Here's how to implement strong encryption practices. Use AES 256 for encrypting sensitive data. Implement TLS transport layer security for data in transit. Store encryption keys in a hardware security module, HSM or TPM. Access control mechanisms ensure that only authorized users can access specific data and system resources. Organizations enforce security using these access control models. Mandatory access control, MAC, enforces strict classification-based access, e.g. military security. Role-based access control, RBAC, grants access based on job roles, e.g. employees only access relevant data. Discretionary access control allows data owners to set access permissions, e.g. file sharing settings. Here's an example. A government agency enforces MAC, restricting access to classified files based on security clearance levels. Employees with confidential clearance cannot access top-secret files. Here's how to implement effective access control. Use RBAC for scalable and manageable access control policies. Apply least privilege principles to minimize security risks. Implement multi-factor authentication, MFA, to enhance login security. Now let's summarize what we've learned about security capabilities in information systems. Memory protection techniques, ASLR, prevent unauthorized code execution. Trusted Platform Module, TPM, secures encryption keys and system integrity. Encryption protects data at rest and in transit using AESA and TLS. Access control mechanisms, MAC, RBAC, enforce security policies. By leveraging the built-in security features of information systems, organizations can strengthen their defenses against cyber threats and unauthorized access. This concludes our module on understanding security capabilities of information systems. Up next, assessing and mitigating vulnerabilities in security architectures. Stay secure.